Okay, there was something that came up here as a comment that I didn't see for a long while because it was marked as spam, which I'm not sure why, because it doesn't look like spam to me. But it was around this one here, 142. And the question is, for the following exercise, decide if the function is continuous to the given point. If it is discontinuous, what type of discontinuity is it? So here, if you calculate f of 1, that would be sine pi over tan pi, which is 0 over 0. Now, it is interesting though, because if I was to graph that, I'll just say sine pi x over tan pi x. It actually doesn't look like it, does it? But in fact, they're exactly at this point here, it's not defined because of the 0 in the denominator. However, it is, although it's not defined and it's a singularity or a pole, I'm not actually sure what the precise correct term is. I can't remember if there's a difference between the two. Whatever it is, it's a removable singularity, because if you went with this definition, fy equals sine pi y over tan pi y when y is not 1, and then 1 when y is 1, then you'll get the exact same graph and there will be no infinitesimal break in the graph right here. So it isn't defined, but the break is removable and easily fixed. However, you need to state this. So the function by itself, like this, not defined at y equals 1, but like this it is. And this comes up because there was a question a student asked me a long time ago. I can't quite remember it, but it was something to do with was something to do with the quotient rule. So he said, or something like, you could say fx equals 1. I think this was, if I remember this correctly. Now, what was his argument? Which you could change as x over x, and then the derivative would be the bottom squared, the bottom times derivative of the top minus the top, which is the bottom times derivative of the top minus the top times derivative of the bottom. And that is, oh, maybe this wasn't quite his argument. 0 over x squared. This is what he was saying. And then he was, I don't quite think I'm doing his argument justice, because then he said something like the derivative at 0, according to this, is undefined. But of course, the derivative of 1 is supposed to be 0. Maybe that's not quite his argument. I don't remember exactly what it was, but I do remember him doing something like taking a function, something simple. Maybe it was the function x he took, but then he changed it into x squared over x, and then he calculated the derivative. I think maybe it was something like that, actually. The bottom squared, the bottom times derivative of the top minus the top times derivative of the bottom. So that's 2x squared minus x squared. Is it 2x squared, x squared over, no, that wasn't it either. Sorry, I don't remember what his argument was precisely, but what I do remember was I was able to pinpoint in his argument the mistake was at this step here. So this function here, fx equals x, and this function here, gx equals x squared over x, technically they're not the same function, because function f is defined on all the reals, whereas function g is defined at all the reals except for 0. So, not technically the same function. This is not defined here. I just thought this is interesting. You've got to be careful with canceling. There's a famous proof uh, where it's something like you prove that 1 equals 2, and it's because you're dividing by a term, not considering that it could be 0. It also kind of reminds me of this. Anyways, I just wanted to make a little video on that.